Hey, feeling good, like I should. When in dark, I walk around the neighborhood, feeling blessed.
Alrighty, let's take a look at our homework for lesson 4.2.2, problems 41 through 45. Directions say on your own graph paper, draw axes, decide on a scale, and plot the points that are over here in this table. Then it asks, does this appear to be proportional or not? So looking at the values for x, it looks like we need to be able to go all the way to 9 on the x-axis. So choose your counting sequence, and I just decided to count by ones, didn't have to go too far. With the y-axis, which are these quantities, we want to be able to get up to about 30 or higher. So I decided to count by fives on the y-axis so we could easily space it out and get past 30. Now when we plot these points, 2, 6.3 is located right around here. 5, 18 point, where is 5? 5 is right there. Oh, why do I have 5 there? That's weird. 6 is 18.9. which is just below the 20, and then 9, 28.35 is somewhere in this vicinity. And when you connect those points, there's my 5 and 15.75. So that looks like it's a little bit beyond the 15 mark. So when you connect all the dots, it looks like the line's going to pass through 0, 0. And if it does pass through 0, 0, and there's a constant growth rate, as shown by having a straight line on the graph, that means that yes, this is a proportional type situation. Now, if you want to prove it that it's proportional, we can do it another way. You can figure out, all right, if this right here is what we call our unit rate, and that should be our multiplier. 2 times 3.15 needs to be 6.3. 6 times 3.15 needs to be 18.9. And we can test that out with the calculator with any, we see it with 2, but let's check it with the check it with the 9. How's that? 9 times 3.15 gives us 28.35. So there you go. You've got a constant multiplier of 3.15. And the third way that we could test it if we wanted to would be to just take any two of these and write them as a proportion. So 18.9 for 6, and let's choose the 5 and 15.75. Now trying to simplify down these two, it would not be very easy. So this is where I would use cross multiplication. So let's make sure that 6 times 15.75 gives us the same product as 5 times 18.9. So 6 times 15.75 is 94.5. And let's take 5 times 18.9. 5 times 18.9. 94.5. There we go. So we have proven this in multiple ways. There's a unit rate, which is the constant multiplier. There is the proportional reasoning, where the cross products of any two ratios are equivalent to each other, which means the two fractions are equal. And then we've got a graph that passes through the origin and is a straight line. All of those indicate, yes, this is a proportional situation. Speaking of proportional situations, it turns out that probability involves proportional reasoning. So a bag of 4 brown marbles, there's 4 there, 3 green marbles, 2 red marbles, and 1 purple are put in, the bag contains that, so put into a bag. So now we're going to take the probability of drawing each color if you were to just randomly pull one of those marbles out of the bag. So we have to count up the total. Remember, there is this ratio for probability, which is the total number of desired outcomes out of the absolute total of everything in the bag. So in this case, 4, 7, 8, 9, 10, all of these have a denominator of 10. And since there are 4 brown, then that would be 4 out of the 10, which is 40%, would be your probability of pulling randomly a brown marble. 3 out of the 10 are green, so the probability of pulling out a green marble is 30%. 2 of them are red, and 1 of them is purple. So there you go. Those are the percent for chances, and these are the simplified ratios for the probability. And you, of course, can convert any of those into decimal numbers if you needed to use those as a multiplier for some reason. Okay, here are diagrams to help us understand what we do when we solve algebraic equations. We know that this quantity here has the same length as this quantity here, so that means that they're equal to each other. Since we don't know the value for x, we're just going to put x's in there, and so that means, we just know that this is considered 4x's, while we know this one is equal to 12, but we know that they're equal to each other. So if each one of these x's is exactly the same, what number do you repeatedly add together 4 times to give you 12 for an answer? Well, that's got to be 3. And so we model this as 4x is equal to 3. And so when you divide each side by 4, you get 1x, right? Because that's a giant 1. 1x is equal to whatever 12 divided by 4 is, would be 3. Here it gets a little trickier because we don't know what r is, and we technically don't know what the complete length of each one of those lines is either. We do know this. We know that this one is the same as this one. So if we were to take away this section, that would give us just 3 r's plus 3 is equal to 21. And if I took away these 3 right here, then that would leave you with 18. So ultimately, we end up with 3 r's is equal to 18. And now we can figure out each r must be equal to 6. Now, how do we prove that each one is equal to 6? Because I'm going to write it in here. 6 plus 6 is 12. 6 is 18, plus 6 is 24, 25, 26, 27. This must be 27. Are we talking feet here? Probably feet, because that's what Cecil always used. And then here, if this is a 6, then 6 plus 21 is also equal to 27. So we can use this as a model to show us why we would remove balanced sets, canceling that out, then remove balanced sets again, that's to this point where we divide both sides by the same number so that we can figure out what 1r is equal to. That is the algebraic process that we will be working on very soon and will be a big part of problem solving that we end up doing for the rest of this year and much of 8th grade. All right, not my favorite questions, trying to show what we're doing here and why we do what we do when we simplify expressions, but we'll just go through the process. Ultimately, if you are getting the correct answers, that is really what we need from you, okay? So knowing why we're doing the steps, that's important too, I guess. So we have to start by sending in the dive bombers there to distribute a property and then simplify. And you can rearrange the terms. Where were they being rearranged? Was it right here? I don't know. I don't like this problem, to be honest with you. That one's a little confusing, but I mean, these are the steps that you would go through. So yeah, you use commutative property between those two and eventually simplify it. Here, we're going to do the multiplication first because that's what order of operations says. And now we can go from left to right, or we can use commutative property. And you see how they did change this when you were subtracting? But technically, they did KFC, even though they didn't show it. The negative is attached to the 8. So as long as you move the negative sign with the 8, this would then become 18 plus a negative 8, so that we could change it back to 18 minus 8, which is 10, and then 10 plus 12 is 22. Okay, so let's just move on to some other problems. Write 3 different sentences that could describe the relationship. So there are lots of different things you could say. First thing I noticed is this is 1/3 of that, and this was 3 times that. So that I took care of that right away. But you could also talk in terms of 81 being $54 more than 27, or you could have said 27 was $54 less than 81. So there were a few different statements that you could make comparing those 2 quantities. And that is it. That is our homework for 4.2.2, under 10 minutes. Good job. Let's move on to our next activity. Take care.
Hey, feeling good, like I should.